Well, hello everyone, and welcome to what will be a very brief video section for you during your online learning this week. We've been spending a lot of time in class talking about sensation and perception in general, and specifically about the visual process and visual perception. And so for the initial part of our online learning, we're going to just take a peek at one last learning target, which is for you to be able to explain the role of top-down processing when it comes to us seeing illusions or things that aren't technically there. We talked about how our mental set can actually influence what our eyes see. And so we're going to look at that for just a moment here together. So as a reminder, our brain actually constructs our perceptions, and it's slightly prone to error. So perception is not just a projection of the world onto our brain. Rather, our sensations are disassembled into information bits that our brain, using bottom-up and top-down processing, then reassembles into its own functional model of the external world. And that's why we don't always agree about what we see, even if we're technically looking at the same thing. So during this process, our assumptions can sometimes lead us astray into us seeing illusions or things that aren't actually there in official reality, let's say. Okay, so as a reminder, top-down processing, we form perceptions or focus our attention by starting with a larger concept or idea and then working our way down to the finer details of that concept or idea. An illusion happens when there's a sensory distortion that can fool our senses in some way. So illusions can involve any of the senses, but visual illusions are those that are best understood by science. They're the most easily testable. And illusions occur when a situation distorts a person's capacity for depth and motion, or for perceptual constancy when we're looking at those perceptual principles. So what we're going to do for the first part of your online learning is you're going to go ahead and pause the video and just interact with a couple of different researched illusions that are out there. And so in your notebook for this particular activity, go ahead and you can just do one or two images. One would be fine with me, you guys. So under each little category there, like motion and time, if you'd like to paste one image and give one explanation, that's perfectly acceptable. If you're really into this stuff and you would like to do both in each area, please feel free to do that as well. But go ahead and pause the video and take a look and interact with some of those optical illusions. And you're going to paste an image and provide a short explanation under each of those major categories. Have a fun time. All right, coming back together, our last little bit of information for this online learning today is about auditory processing. So we've spent the past couple of times looking at visual processing. Now we're going to look at auditory processing. And similar to the information related to vision, we want to have a solid understanding of the major structures of the ear and the process of auditory transduction. So how do sound waves become transduced into neural impulses that our brain can then understand? Okay. So just like the visual wavelengths that we talked about last time, we're going to talk about sound energy today. Okay, so the sense of audition or hearing results from sound waves created by vibrating objects being converted into neural messages. And sound waves, just like light waves, have three physical dimensions that we look at: frequency, amplitude, and complexity. And so you can see here that the frequency or the length of a sound wave determines the pitch that we hear, either the highness or the lowness of a particular sound. So waves with low frequency produce low-pitched sounds like a foghorn or my deep voice right now because I'm not feeling very well. High frequency waves produced high-pitched sounds like Elmo from Sesame Street. That was weird, but hopefully that entertained you for a second. You get the idea. And so I would encourage you to just do some tests with yourself and think of your own examples of what are some low-pitched sounds, some low-frequency sounds in your life. What are some high-pitched, high-frequency sounds? We also have wave amplitude or height. And that determines the loudness of the sound that we hear. So a high amplitude wave produces a really loud sound. and a low amplitude wave produces a really soft sound. And finally, we have wave complexity, simple versus complex, and that relates to timbre or sound fullness, the richness of the sound that we hear. Okay, so we're going to briefly talk about the pathways that these sound waves take when they travel through the ear. But first, here's a diagram of the ear for you. And what I would love for you to do is pause the video here and use this diagram to follow the directions in your notebook and complete the diagram there. So go ahead and do that, and then we'll come back together. All right, so let's talk about how these sound waves are transduced into neural impulses that the brain can understand. So first, sound waves enter the outer ear, which collects the sound and funnels it to the eardrum. For each of these ear structures, then you can go ahead and put the corresponding function into your interactive notebook. So the outer ear collects sound and funnels it to the eardrum. The pinna, which is the visible part of the outer ear, specifically collects sound waves from around the ear and directs it into the outer ear canal. Then the sound waves reach the middle ear. In the middle ear, the sound waves hit the eardrum and move the hammer, anvil, and stirrup, those bones, super cool named bones in the middle ear, in ways that amplify the vibrations of the waves. And then the stirrup specifically sends those vibrations to a structure called the oval window of the cochlea. In the inner ear, then, waves of fluid move from the oval window over the cochlea's little hair receptor cells, and those cells send signal through the auditory nerves, eventually to the temporal lobe of the brain. So vision goes to the occipital lobe, auditory information goes to that temporal lobe, like we learned about in the brain chapter. The eardrum is a thin membrane that vibrates when sound waves reach it. And then the cochlea itself is this spiral-shaped, fluid-filled inner ear structure. It's lined with those tiny hairs, they're called cilia, that move back and forth when vibrated. And the movement of those cilia cause a nerve impulse to form. So super important concept to remember is that transduction technically occurs in the cochlea. Sound waves are literally changed into neural impulses in the cochlea. Once those are formed, then we have auditory nerves that carry those signals again from the inner ear up to the brain. And that's what we've got. Next time in class, we're going to talk about your vestibular sense. And so just want to preview for you this structure called the semicircular canals. These are 3 loops of fluid-filled tubes that are attached to the cochlea in the inner ear, and they help us maintain our sense of balance. If you've ever had vertigo, I'm so sorry because that's a terrible feeling, but all of that's controlled for based on the positioning of the fluid in those inner ear canals. All right, so we're going to pause real quickly, and I just want you to take a moment to check your own understanding of the auditory process of transduction. Okay, so in your notebook, just like we did with vision last time, you're going to see the steps of transduction. And what I would love for you to do is drag and drop those into the correct order in your notebook. So go ahead and take some time to do that now. Last little bit of information related to hearing and sound. Let's talk about loudness for a moment. So loudness refers to more intense sound vibrations. We learned that. And this causes a greater number of hair cells, those cilia in the cochlea, to send signals to the brain. Soft sounds only activate particular cilia or those hair cells in the cochlea, but louder sounds move those hair cells and their neighbors. When we think about pitch, a little bit more about pitch, how does the inner ear turn sound frequency into neural frequency. So again, we talked about those wavelengths coming into the ear and being transduced into neural impulses. How does that transfer? There's two different theories that seek to explain how that occurs: frequency theory and pitch theory. So frequency theory says at low sound frequencies, hair cells send signals at whatever rate the sound is perceived. Place theory says at high sound frequencies, signals are actually generated at different locations in the cochlea, depending on pitch. So the brain reads pitch by reading the location of where the signals are coming from. Okay, and then finally, how can we tell when we hear sounds in the world around us where that sound is coming from? We typically do a pretty good job of that as human beings. And so the way that that kind of happens in our brain is that sounds usually reach one of our ears sooner than the other one and with more clarity. And that's what tells our brain where the sound is coming from. The brain can then kind of use that difference to perceive, I heard it more clearly and quicker on the right side, I'm going to look to the right. You can trick people by trying to create sounds right directly in the back of their head or on top of their head. And then it's really difficult to know exactly where a sound is coming from. So I don't know if you've ever had the experience of a fire alarm going off in your house, and because it's above your head, it's not hitting one ear before the other. And you're like, which one is it? Where is it coming from? So that would be one example of that as well. Okay, last thing we're going to look at together is hearing loss. So we're going to talk about the difference between conduction hearing loss and sensory neural hearing loss. Conduction loss is when the middle ear isn't conducting sound well to the cochlea. There's an issue with those bones in the inner ear, and the transduction process is being hindered in that space. And so the necessary information isn't making it to the brain, so the brain can't perceive sound. The sound is entering the ear, but it's not making it to the brain because of the issue with those bones, okay? Sensory neural hearing loss is when the receptor cells themselves in the cochlea are not sending messages through the auditory nerves. And so again, sound is entering the ear, sound information, sound waves, but it's not being transduced and sent to the brain for further processing. People with conduction hearing loss can be helped with hearing aids because they amplify the sounds striking the eardrum and keep the sound wave moving into the cochlea where it can then be further processed. But people with sensory neural hearing loss can benefit from a cochlear implant, and that implant then does the work of the hair cells in translating sound waves into electrical signals to be sent to the brain. So just want to know the difference between those two types of hearing loss and how we would treat those differently to make sure that auditory processing can happen. Okay. Last little thing, I'm going to sound like such a mom to you guys right now, but you definitely want to be really careful of your ability to hear. Lots of research shows that if we expose ourselves regularly to sounds that are occurring above a particular decibel level, we can cause irreversible damage to our ability to hear, either through the structures of the inner ear or because if you hear sounds that are too loud, a lot of times they cause the cilia in your ear to move back and forth so quickly that they actually fall out and they don't regenerate. So be really careful about the noises that you expose yourself to because they can cause lifelong damage. That is it for today. I hope that you have a marvelous rest of your week, and I look forward to seeing you in class really soon.